It was January of 2005, and Dorry and I were newly married.
Sommer was finishing her PhD thesis at MIT, and I was training in transplant surgery at Johns Hopkins. One day when she picked me up from work, we had an interesting conversation.
It was a conversation about math and medicine.
A conversation about expanding kidney transplants.
Using integer programming and graph theory.
A conversation about creating a husband and wife collaboration
to solve a problem uniquely suited to this husband and wife working together.
You see, now this may come as a shock to you, but transplant surgeons don't usually talk to mathematicians.
And mathematicians don't usually talk to transplant surgeons, probably for the same reasons.
But it turns out that this conversation would save thousands of lives and fundamentally change the way we think about kidney transplants.
In fact, Dorry had just finished a kidney transplant. Actually, 2 transplants, where the donors had agreed to exchange kidneys.
Exchanging kidneys was kind of an unusual concept at the time. Here's how it works. If you have kidney failure, you either go on dialysis or you get a kidney transplant. You'll live twice as long with a transplant, so that's the better option. Now, if you want a transplant, one option is to sign up for the deceased donor waiting list. The problem here is that you're not the only one with that plan. In fact, 100,000 other people had that plan before you, and you get in line behind all of them. So you might wait 10 years for a kidney, you might get very sick, or even die before you ever get a kidney offer. That's pretty depressing.
But you might have a friend or a family member willing to donate to you. This gives you 2 advantages. The kidney lasts twice as long as one from a deceased donor, and you don't have to wait in line, so you don't suffer the consequences of years of dialysis.
The thing is, you have to be compatible with your donor, both blood type and HLA compatible. Blood type compatibility, that's like when you donate blood. O is the universal donor, but an O recipient is born with antibodies against both A and B, so is incompatible with any other blood type. HLAs are like little proteins that sit on your cells, including those in your kidney, and people can have antibodies against these proteins too. Antibodies are bad and cause rejection of the organ, so you need to be both blood type and HLA compatible. And if you are, that's great. We can do your transplant immediately. But there's about a 30% or higher chance you won't be compatible. And if you're not compatible, you're pretty much relegated to that waiting list behind those other 100,000 people. That's pretty depressing too, both for you and your loved one who wants to save your life by giving you a kidney.
But at Hopkins, they had a way around this.
So my boss, Robert Montgomery, would find incompatible pairs who were reciprocally compatible and have them exchange donors. So for example, this person can't donate to his loved one, and this person can't donate to her loved one, so instead they exchange, and this person donates to him, and that person donates to her, and 2 compatible transplants result. Voila.
Of course, you need to find matches that are reciprocally compatible, and that can be hard to do at one transplant center where there aren't that many incompatible pairs to mix and match.
But there are hundreds of transplant centers around the country, and therefore thousands of incompatible pairs. If we could create a system where transplant centers work together, lots of pairs could find matches, many more than could happen through just one transplant center.
And that's where math comes in.
The issue is deciding who matches with whom so that you get as many people transplanted as possible. Now, when Hopkins was just mixing and matching within its own patients, this was simple enough to decide. In fact, our coordinator, Janet, just used a magnetic board to find the matches.
But when you're thinking about matching up hundreds or thousands of patients, this requires mathematics, namely operations research, which is the discipline of applying advanced analytical methods to help make better decisions. Operations research, for example, finds the quickest driving directions, designs the least expensive airline routing, and helps sports teams decide when and where to play.
But unfortunately, not how to play. Anyway, I had studied operations research a little bit when I was a computer science major in college, so I knew we would have to turn to this field. And I knew we were very lucky because this was exactly the field Sommer was in. So in our 5-minute car ride, I explained the problem to Sommer.
And it was clear to me we could solve it together.
And then we parked the car, looked at each other, and said,
well, I guess we're going to be research partners.
Now, this was not something to endeavor upon lightly. I mean, we were life partners, and really good ones. We worked hard, had fun, and were generally very happy.
We were also dance partners.
That's actually how we met.
We did really well as dance partners. We choreographed routines. We taught and competed and performed all over the world, and we even won 5th place that year in the American Lindy Hop Championships.
But working together, I mean, being work partners, that's an entirely different thing. So do we take the risk?
Sure.
Why not?
The question Dorry posed on our car ride home led to an entirely new focus area of mathematics and transplantation.
Now people actually refer to Sommer as a transplant mathematician, or at least that's how she refers to herself. So what I'd like to do is have Sommer take us on a little journey into some of the math underlying kidney exchanges so that we get a sense of the elegance and complexity here.
He's trying to say math is cool. So imagine every incompatible pair in the country gets together and says, okay, match us in the best way possible. How do we decide who matches with whom? After all, some pairs are easy to match and have a huge number of potential matches in the pool, but others might have only 1 or 2 pairs with whom a match would work. And these decisions are inextricably linked. We can't assign a match for any one pair without considering every combination of matches possible. So we turned to operations research and graph theory.
Now what you're looking at are a series of graphs. In each graph there are vertices, those are the circles, and edges, those are the lines that connect them. In the context of kidney exchanges, a vertex represents one incompatible pair and all the information we need to know about them in order to determine if they can match with another incompatible pair. We draw an edge between 2 vertices when such a match is possible.
The graph illustrates how every match affects every other match opportunity in the graph.
Now you might think you can just find one possible match, do the transplant, and then look for another match, do the transplant, and so on.
Actually, there's a problem here. Notice that once we do this very first transplant, we reduce the opportunities for everyone else in the pool, and this won't get you to the largest number of transplants. Instead, we have to look at the whole picture and choose the best combination of matches available in the pool. Even with a fairly small group of incompatible pairs, there might be an extremely large number of different combinations of matches. And with 100 pairs, there are about 1 million different combinations. And with 1,000 pairs, there are actually 10 to the 250th power combinations.
Yep, that's a 1 with 250 zeros after it.
So you can see where the challenge is in finding what combination will get the most people transplanted.
And that's where integer programming comes in.
Integer programming lets you maximize an objective, stated in mathematical terms, subject to a set of constraints. For example, let's say you have only $5 to buy lunch. That's your constraint. But with the $5, you want to eat as much protein as possible. That's your objective.
Now the same concept can be used for finding the best kidney exchanges from a pool of incompatible pairs. The key is to translate what you know medically into mathematical terms. Use the mathematical tools to solve the problem, and then translate the math back to the medical world. Let's start with a very simple example. We have 4 pairs, so we draw a graph with 4 vertices. Now let's say pairs A and B are a match, B and C are a match, and C and D are a match, but A and D are not a match, and so forth. So our graph has 4 vertices, but only 3 edges.
Then we assign binary variables x1 through x3 to those 3 edges. These variables will be 1 if that edge is used. In other words, if the ideal combination of exchanges includes that particular edge, and a 0 if not.
We also need to teach the computer some biology, which might be intuitively obvious to us, but not to the computer who is looking at the whole thing as a bunch of variables and numbers. Since the donor in pair B, for example, can only donate 1 kidney, B can't simultaneously be matched to both A and C. That's a constraint. We have to express that in mathematical terms, that x1 plus x2 can't be larger than 1.
We also have to express how many transplants get done. Remember, x1 is an edge representing 2 transplants. So 2x1 plus 2x2 plus 2x3 is the number of transplants that occurs. So in a maximum cardinality matching, the objective is to maximize this expression subject to these constraints. Solving the integer program means deciding which of the x's should be zeros and which should be ones, which means deciding which kidney exchanges go forward.
And in this simple example, we can obviously see that the best combination of matches involves A with B and C with D. If we had just matched B with C, then A and D would have been left out in the cold.
But things might not be so simple, and we need to consider other factors in the objective, in addition to getting the largest number of transplants.
Let's take the same example but add one more edge.
Now, there are two possible matchings. Either AB and CD like we showed before, or AC and BD. So which do we choose?
What if, true story, patients A and C are from one transplant center, let's say in Baltimore, and patients B and D are from another transplant center on the other side of the country, let's say in San Francisco. If we choose to match AB and CD, now we have two matches that require transplant centers that are thousands of miles apart and in different time zones to work together to organize these transplants.
But if we choose to match AC and BD, now the Baltimore matches stay in Baltimore, and the San Francisco matches stay in San Francisco.
This might seem trivial in the simplified case, but you can imagine that with hundreds of transplant centers and thousands of incompatible pairs, if we didn't pay attention to minimizing distance and travel, things might get very complicated.
The key is adding weights to the edges, moving from maximum cardinality matching, which considers only the number of transplants, to maximum edge weight matching, which also considers the quality of the matches.
We can assign the weights in any way that we feel is right, giving priority to things like matching within your own center or a match that involves a pediatric recipient, etc. We translate our priorities to points and then assign those points as edge weights on the graph. For example, if we gave 100 points to every transplant, but an extra 10 points if an exchange happens within the same center, then the match between A and B gets 200 points because the recipient in A and the one in B get transplanted. But the match between A and C gets 210 points because in addition, we facilitate a match that happens at the same transplant center.
Then, our integer program is rewritten to reflect these edge weights. Instead of adding up the x's, we do a weighted sum of the x's. Since the binary variables are 1 if that edge is used and 0 if that edge is not used, the objective amounts to adding up the weights of the edges that are actually chosen.
So far, we've talked about only two-way matches. One limitation to two-way matches is reciprocality. In other words, the donor for A has to be compatible with the recipient for B, and the donor for B has to also be compatible with the recipient in A.
But what if we consider three-way matches, or four-way, or five-way?
Now, don't get too excited there.
To accomplish this, we need more information. Before, we only drew an edge if A and B were reciprocally compatible. So one undirected edge is equivalent to two directed edges. Now imagine that A can donate to B, but B can't donate to A, so a two-way exchange isn't possible. But if B donates to C and C donates back to A, then 3 recipients get a transplant.
A cycle in this graph, be it two-way or three-way or four-way, represents an opportunity for all the pairs in the cycle to donate and receive a compatible transplant.
So the integer program now has one variable for every cycle in the graph, instead of one variable for every edge. Now x1 and x2 and x3 can represent cycles of different lengths.
But even with sophisticated math, we run into limitations of biology again. These incompatible pairs are very likely to have blood type O recipients with A donors, because an A donor cannot donate to an O recipient. Remember the whole thing about blood type compatibility. On the other side, there will be almost no O donors with A recipients, because usually that's a compatible donation. So there's a blood type imbalance that makes it impossible for many of these pairs to find a match.
At best, from a pool of incompatible pairs, we predicted that fewer than half would find a match opportunity.
So we sought new pairs to bring into the pools. One answer was to invite compatible pairs to participate in exchanges. By compatible pairs, I mean people that could otherwise just donate to their loved one without participating in something like this. They don't need an exchange. But
the compatible pairs might gain something from participating. For example, they might find a younger donor in an exchange.
Or they might just feel lucky that they're compatible and want to help another family in need. Regardless, these compatible pairs have a huge impact on the number of exchanges that can be accomplished because they can fill the shortage of O donors that otherwise limits match opportunities for incompatible pairs.
There is a nice graph theory tool that works perfectly for the compatible pair. It's called a self-directed edge. In the context of kidney exchange, a self-directed edge indicates that the pair has an option to do a direct donation. The self-directed edge gets put into the optimization, so the vertex with the compatible pair will only be incorporated into an exchange if the exchange allows a higher objective, like a larger number of transplants.
We can also ask non-directed donors to participate. A non-directed donor is someone who comes forward to donate without any intended recipient, just wants to help someone who needs a kidney. Believe it or not, there are hundreds of folks like this. Some people call them altruistic donors, some people call them good Samaritan donors, but from a purely practical standpoint, they're people whose donation is not directed to a given recipient. What we used to do is give their kidney to the person at the top of the waiting list, and one person would get transplanted, which is, of course, always a good thing.
But if a non-directed donor gives to the recipient of an incompatible pair, then that pair's donor can give to another incompatible pair, and so on. The non-directed donor solves the problem of reciprocal compatibility, because there's no requirement at the end of a chain of donations to make sure the last kidney matches back to the non-directed donor.
So now this gift is multiplied. The non-directed donors are thrilled to learn that their one donation enables 2 or 3 or even 30 people to get transplanted. And then, at the end of the chain, a kidney still goes to the person at the top of the waiting list.
And all of these expansions go right into the graph and the integer programming model, so that a heavy-duty computational solver can search a huge space of potential answers and find the combination of matches that gives the most benefit.
And it's a good thing we have these mathematical tools to turn to because, like we discussed back in that car ride in 2005, kidney exchange is an exploding field. The year we started this work, only 30 patients got transplanted through an exchange, and only a small handful of centers were actually doing this. Since then, several thousand patients have been transplanted through an exchange, and this is now offered at more than 100 transplant centers. Congress even passed a bill formalizing the role of kidney exchanges.
Every one of these exchanges has brought new kidney donors into a system that desperately needs them.
Working together as husband and wife to make this happen has been incredible.
I love explaining to math majors that they should study integer programming so they can save lives with it. I mean, who wouldn't want to become a transplant mathematician?
Yeah, who wouldn't? Okay, fine. I also love knowing that I didn't waste my degree in computer science by going to medical school. It amazes me how much we can improve healthcare delivery through a robust analytical approach.
And of course, the story's far from over.
Sommer finished her PhD at MIT and is now tenured mathematics faculty at the Naval Academy.
Dorry finished his transplant training and now works as a transplant surgeon and runs a big NIH-funded research group at Johns Hopkins, answering all sorts of questions about outcomes, disparities, and policy in transplantation.
As collaborators, Sommer and I keep using optimization to improve other areas in transplantation.
For example, there are huge geographic disparities in the availability of liver transplants in this country.
See, a liver from a deceased donor must be transplanted relatively soon after it's recovered, so livers are typically allocated to nearby candidates. But history left us with some allocation regions that have higher supply and lower demand, and others that have lower supply and higher demand. So the problem is patients waiting in some regions have a much higher chance of dying on the waiting list than those in other regions.
Using an integer programming model, not all that different from the one for maximizing kidney exchange, we're now designing new boundaries and totally new allocation districts to minimize the disparities between organ offers for candidates in different districts. Redistricting is another approach from the discipline of operations research. While redistricting has traditionally been applied to voting districts or school zones, we're now poised to apply it to organ allocation.
So I guess we're pretty glad we took the plunge to become not only life partners and dance partners, but also research partners.
It's a huge advantage for us that we can discuss modeling details over spaghetti at dinner, or write a paper when we get stuck with an airport layover, both of which we've done, true story. But the real win is being able to share the intellectual excitement of math and medicine with your spouse at a deep level. Because I think we just admire each other more and more as we build these ideas together.
Yeah, what she said.